It should just record to my account so that I can upload it to YouTube. Is
Done. I did it.
done.
Okay,
All right,
done?
great.
Okay, great. Oops.
Oh,
All right,
we're off.
great. So we're off. Hi everybody, I'm RJ. And we're going to talk about this paper. I hope people had a chance to at least pick through it. I know this is one of the hardest papers I've read in a long time. So I understand if you didn't understand everything that's going on. I certainly didn't. And I had to dig through a bunch of other papers to have the context also to understand it. So, and then there's a lot of proofs that are like take too long to read and are not as important to understanding the paper. So like there's a lot there. But without further ado, this sCM, there's a simple, stable, and scalable, and they actually the authors do a great job of actually going through all three of those things in the paper. The consistency model, we'll talk about what that means in a little bit, but that's CM. And then like, why are they doing this? Well, because these continuous time consistency models show promise, but they're hard to train and hard to scale. So the paper kind of presents some techniques for getting over those challenges. Okay, so I'm gonna, as me and Swix were talking about in the beginning, I think it is good to have just a recap of diffusion in general, and this is more complex version of diffusion, but I thought a lot of people have seen this diagram, so it'd be useful to talk about what we're talking about here, and in reference to sort of stable diffusion and latent diffusion. So the sort of the left space is the variational autoencoder, and that lifts the pixels into latent space. So we're not going to talk about that. And then the right-hand side is the conditioning on images and text. So that's how you actually prompt the model instead of just generating random images. And so we're also not going to really talk about that. But suffice, these mechanisms are they're compatible with the existing technologies for these things. So you can just view it kind of as a drop-in replacement for the screen part. And actually, we'll keep this diagram in mind. The UNet in the middle, the big part in the middle with the attention blocks there is basically identical even. So a lot of this diagram is the same. And it's really about the training process and some tweaks to make the main network work well with that training process. And specifically with the regular diffusion models that we all know and love, they have to iterate multiple times generally to generate a good image, whereas these consistency models are designed so they can generate a good image with only one pass through the network, and there's a mechanism by which you can iterate to refine if you want to, but the idea is that you don't need to even one shot through the network is enough to get a really good image. And I tried to put all the links that I took images and other things from, so I'll share this and everyone can click on those if they want. So please, and also please, if you guys have questions, I know they go in the chat. I'm not watching the chat, so let me know if you want to interrupt and ask a question. This is just regular diffusion, and the idea is quite simple. You're just adding step by step some amount of noise, and this is actually scheduled. I learned this that it's not actually it's it's not adding a constant amount of noise at a time. It does work that way, and so the top image is like that. They found in this paper that it's actually inefficient, that you end up with a lot of wasted backwards diffusion steps that you don't need, and you can cut out a whole bunch of it just by using a cosine schedule. So the intensity of the noise is modulated by this cosine. Yeah. And then I think this is where it gets interesting, the reverse diffusion process. And I actually learned a little bit about this during when I was studying this, because my impression was that you sort of like crank in the image, and then it just sort of like progressively refines and refines and refines, but that's not actually quite what's happening. And this diagram here kind of shows this, and so we're gonna have to look at the next one to really understand what's going on here, maybe fully. But if you look on the right, maybe starting on the right, you see that like the predicted noise at every step is actually like you can't really make any sense of it, right? It's all just noise. And then the middle column, you have like slightly more more and more refined picture, and then on the left you have this like sort of full noise removed column. And the weird thing is that like if I look at for example on the t equals 40 row, and then I look at the t equals 30, the full noise removed, that doesn't look like the one in the full noise removed column looks a lot more refined than the one in the input at t, right? And so like in the 30, you would expect 30, the output at 30 would be more than like nicer than the input at 40. And it's actually not the case. And the reason is because that's not exactly what's happening, right? It's not the output goes into the input, but rather the input is only being used to improve the noise estimate that's in the right-hand column. So that noise estimate is added to the noise in the like from the like sort of generated noise. It's added, the right-hand column is added to that generated noise to get the left-hand column. So and the middle column is only input to the model in order to refine how to generate that. Is that, I want that thought to make sense. And I'll switch to this page, but if anyone wants to ask a question, that now would be a good time. Because I think, and I try to illuminate a little bit what's happening here. But I want to, okay, so I'll please interrupt if you want to ask about this.
It's good so far, Jay. Go for it.
Okay, great. So now what's happening, and this is sort of like a bad illustration of the same concept, but in a different way. So that if you look on the t equals 10 right-hand column, that's like just random noise that was generated as input into the model, right? And then on the right-hand column, you have denoised versions of that noise. And so if you look at like, let's look at the bottom t equals 8, right? So time goes kind of backwards here. So left hand is t equals 0, right hand is t equals 10, and then t equals 8 is 2 to the left of t equals 10. And so because the backwards diffusion process goes backwards in time. So that t equals 8, what's happening here is that the line, the thing at the top of the line is actually the input to the model. It goes through that thing with the attention block, and then it outputs something to add to t equals 10. And then when you add those two things together, you get the thing at t equals 0 down at the very lower left. Right. So then as time goes on, we get to t5, and we have a better estimate of that noise because we've gone through several steps. And then we add that to the t equals 10, and we get that airplane that's kind of blurry in the top left. And then t equals 3, and then finally we get to something that's really close to the original data. So and I'm making this distinction because it's very different. I hope this is clear, because it's different than, this is sort of the motivation for how to understand what's happening with these trajectories in the paper, is that you can see that these are separate trajectories, and I've intentionally drawn that. It's not just like me being inaccurate. I've intentionally drawn it that way because the locations that you're learning are not basically on the same trajectory in this latent space. They're not in the same trajectory as each other, right? So that like, and this causes a lot of inefficiency, and that's sort of the whole point to these consistency models and other flow matching and other things that use this technique is to sort of like be more efficient about the places you're sampling.
Ajay, and you're saying that the trajectories are not the same. Like t equals 8, t equals 5, t equals 3, they're not on the same trajectories on each other, in the sense that with t equals 3, you could not have gotten what you have gotten at t equals 5.
That's right. That's right.
No, don't restart your computer.
Yeah.
Yeah, okay. I understand the intuition. Thank you. And why is that?
This is slightly vague in my mind, but basically because all that maybe I've drawn them like further than they might be in reality, right? They'll probably be pretty close, but the point is that when the input to the model is like the t equals 10 and the t equals 8 noise at the top, right? And that doesn't necessarily and I'm just trying to generate something that I can add to t equals 10 to do a little better than that t equals 8 one, right? So I didn't draw this, the lines are on the square, but I'm trying to generate this thing. And so there's nothing constraining it in the latent space to be on that same trajectory. So it doesn't necessarily pick something.
I see. So each trajectory at T8, T5, T3, they each try to optimize as much as they can, and therefore they arrive at different. That's the intuition. Thank you.
Yeah, they're always like this t equals 3 is just trying to get this like little fuzzy airplane noise back or something like that. Not the fuzzy airplane. Sorry, I misspoke. Just some noise that produces something like that corresponds to that fuzzy airplane thing. Does that make sense? A little bit.
Yes, it does. Thank you.
Okay, great. Okay, so this fancy plot is sort of the alternative that I just alluded to, and we're not these stochastic differential equations. We're not going to really talk about this, and this is like a thing that you don't really need to understand. So I just got it from this diagram, so you can just kind of ignore the SDE part. It looks almost the same. It's slightly different. Doesn't really matter, but it's actually a cool diagram because you can see this. There's these stochastic differential equations that are like sort of modeling this random process by which, sort of you have noise, and it has a continuous instead of a discrete. It's a continuous instead of a discrete process. So like adding noise to like on your left-hand side, very, very left is the data, and these two like normal looking distributions. So this like bimodal normal distribution. And then what this differential, so this is sort of like heat diffusion, right? And as time is going to the right, and as the sort of like heat that is sort of condensed in the modes of these two Gaussians, like over time, it kind of spreads out and ends up, sort of like in the middle with this prior here. And that's not exactly what happened, because it's not quite this, it's not the heat equation, but like it's a useful intuition for what's happening here. So that like there's some differential equation, and it's describing this like sort of diffusion process by which everything ends up in this sort of like literally Gaussian prior for the distribution. And so this is where we generate our noise, and then we use the backwards process to get back to these, these distributions, these bimodal distribution. And there's like each one of these squiggly lines is a trajectory from that some random process could have taken based on the sort of likelihood that is imposed on the field by the diffusion process in the colored diffusion process in the background, right? So and then this probability flow ODE is sort of a deterministic version that looks at what is the maximum likelihood path if I started at that trajectory, right? So in this, so like looking at, the easiest one to see is this bottom white one. So if you look, what this is saying is I started here, what is the maximum likelihood path for me to get to somewhere in this middle area, right? So instead of like so you can imagine if I sampled like a huge number of these SDEs, and then I took each one of these columns, I took the, sort of the means, then I would get, if I started here, I would sort of follow this path, right, to get to this point. I'm not speaking super accurately, but that's sort of the intuition. So, okay, so, this looks quite different from what this previous diagram, but it's actually the same kind of space. So I want to, so in this diagram, you would have like, maybe a chunk right here, which is, like I did a discrete Gaussian blurring of my data, and then I did another one and another one and another one. So this is discrete. And so what happened, this is what happens if you just make the number of those discrete discrete Gaussian blurrings infinite and infinitely small. Okay, so and then the other thing, just to look at this is a score function. We don't have to really understand it right now, or not too much ever in this talk, but the score function is more or less, this is sort of how this is the mathematical mechanism by which the reverse diffusion can happen. And inside of this score function is our UNet model, right? So our UNet is there. And so I'm using that UNet to predict what's called the marginal distribution on that probability for that data. And then that's what helps it to sort of figure out how to do this process in reverse. Okay. I know this is not super clear. Hopefully it will become slightly more clear. And then just to be clear, this is like a UNet. This is I don't think it really matters, but this is like the name of the particular UNet model. And then this is sort of what I just said. It estimates a gradient of the log probability density with respect to data at a given time step. But most importantly, that's where your UNet lives. And then this works in latent space too. So this is like all the other stuff that is in that first diagram. That's all here in the left-hand side. Okay, good. So now let's talk about consistency model. So you can see this looks a lot like this, but it's slightly different, right? The same author, so not surprising. But so this is sort of the left-hand side, right? And then we got rid of all the squiggly SDE stuff. So so what's happening here, and this goes back to the discussion about trajectories. These are trajectories. So you start, in the forward direction, you start at one of these green dots, and then you follow this trajectory, and you end up somewhere in this noise distribution here, so that like this structured data turns into a Gaussian distribution. And what are so we have this a particle function, ordinary differential equation. I think it's particle. It could be probability function. I think it's probability. And it sort of is a differential equation that can map from a given point here back to a given point here. So then we can do that because since it's deterministic, then there's exactly one for any one place here. There's exactly one place here, right? So because you have that, what a consistency model does is it says that everything should be on the same trajectory, right? So if I estimate it, I'm gonna learn how to map from any point on this trajectory to the to this point in the data. So including these very left-hand things. And you'll see that it's useful to be able to map to the middle in a minute. But the point is that the differential equation solver tries to find the parameters of the differential equation such that if I know this, then I know this. Okay, and the link, if you want to learn about that, that's the sort of the first link about that. And then, so just to tie it, I want to just tie this back to, this is the same information, even the same paper, but I just want to tie it back to our, sort of noising and denoising idea, is that we're, sort of like mapping. So this is one trajectory. In this case, it's straight, but like this is one of those curvy trajectories from the previous diagram, and it's mapping back to this data, this image at x0. This is the data that this particular noise best corresponds to, right? So so the idea is just that I'm mapping all the way from any point on that trajectory. And then this is why it's useful to be able to map from any point in the trajectory, is that now I can, if I want to, and most of the time it's 2 times, but if I want to do like refine my image by throwing more compute at the problem, what I can do is I can add sort of these time steps. I can divide my space up into time steps, and then I can sample noise. I can re-add it to the trajectory at that timestamp, and then I can refine based on that noise, and that seems to help the model sort of hone in on the, like, just having another opportunity to refine. It'll put it on a slightly different trajectory and help the model to learn from a closer space what the original data was. So, like, for example, let's go back here. I might, step 1, I start at t, I have this noise, I go all the way to x0, but then I add back enough noise to get back to this step here, and then I follow the trajectory that lands me on. So I will be like slightly off this trajectory. So maybe this is a better model. Like, you think multiple trajectories, maybe I end up on a different trajectory, and that's not what this diagram is for, but I'm end up on a different trajectory so that my data is slightly different. The data that I'm that I'm outputting is slightly different. So I want to just, any questions in the comments? Should I keep just plowing ahead, or do people want to comment or ask questions?
I'm not
No?
seeing any questions in the comments. Other than what are some good open source models? I don't know if you want to chime in on that, RJ.
Yeah.
Especially
there's actually
that can generate images with good text.
I'm actually not the best person to answer that. I think that like the SDXL3 and Flux, but those are not this type of model, I don't think.
Perfect. That's what Alexander suggested as well. And then you would add your own text LoRa's.
Yeah, exactly. Flux is great for text, as well as SD 3.5. Additionally, you can always add some LoRa's. There's plenty of LoRa's on CVTI for making better text. Yeah, I can do this right now. Actually, I have ConfUI open, so if anyone wants to test, I can just throw the text and generate some images quickly.
Awesome. So like, but I think there's maybe this is actually a slightly good talking point. So these types of models are not like these consistency models, and there's like related models. I with the exception of maybe some of the closed sourced models from, I think that, well, a lot of these papers come from OpenAI, so I suspect they're maybe using some of these techniques, maybe. So, and I haven't really looked at the sort of big models that are out there to see if any of them are using any of these techniques, but like this is pretty cutting edge research. So none of this technology that we're discussing today is in any of the big models that we know and love, with the maybe with the exception of Flux. I don't, but that's actually a great question. I'm going to look into that as soon as this is over. Okay, so let's keep going then. So this is now, so these ODE solvers, they're discrete time solvers. So they sort of chunk up the time into little chunks, and then they solve the ODE as best they can given the discretization, the quantization, but that can cause errors. And so that's what this diagram is trying to present, is that if you have like if this delta t here is very big, you see it goes like far from xt to x minus delta t, then the error that it can have is very big, and that can put it on a different trajectory. So you get the wrong trajectory. And then if the discretization is maybe a bit smaller, then the error might be a little bit smaller, and then you'll get a closer but not the same trajectory. And that's sort of the point. And then like in continuous time, in theory, then because your discretization is infinitely small, then it's like quote unquote impossible to get on the wrong trajectory, although there are still obviously ways that you can. But that's the theory anyway. So, and this, I was a little scratching my head a little bit. I didn't see the ODE solver, the continuous models don't use an ODE solver. They do actually in the paper reference using ODE solvers in certain steps, but they're not essential to the process here, is I think the point that they're making. And this unbiased estimator, they don't give any information on how to do this. So I think that what they just mean is an empirical estimation of the marginal distribution, but they think they left that as an exercise to the reader or somewhere in the appendix that I didn't see. Okay, so I'm going to get very mathy for a minute. I know I understand that, like, first of all, even, the math geniuses among us might have trouble following because there's just too little context, and unless you really read the paper carefully, you're not gonna be able to follow super well. But so I want to just call out a few things, and then they're like these equations 1 and 2 are going to reference a little bit to explain how they accomplish what they did, and also these there's this is sort of this canonical equation that everybody has been using. And when I say everybody, I think I mean mostly this same author in previous papers, but also some other people. And so that like this is sort of like the canonical setup. And then there's these constraints that are on the C skip and the C out. And the interesting thing to note, and the reason those are there is that, so if this is the time variable, this C out and C skip, and if time is 0, that means that you have the data, right? And C out, you have none of the input from your neural network, right? So this is just saying at time 0, this is a way to guarantee that at time 0, you're getting back your data. And then the skip and C out, they just trade off in some way between each other. And as time gets later, then you have more, then you are giving more weight to the neural network. Okay. And then this is just, I don't think we need to go through this in any detail. This is just the training objective. And then if you look at this equation 2 is just that, sort of instantiated with this certain kind of distance function. So you'll see that a distance function appears here. This, L2 norm, this L2 loss is being used, which is just squared error loss. That's being used, and then you sort of plug everything in. You sort of take the limit as t goes to 0, or delta t goes to 0, and you get this thing out, and there's a proof of it elsewhere. And this this tangent function is kind of the main actor here. So like you don't really have to care again what this is. Just if you see this thing, or if you see like this delta maybe, then think tangent function mostly. Okay, so I know that this is like probably like pretty opaque. I would be surprised if it wasn't unless you read the paper carefully. And then you know, again, reminding you, this is great, but it has a problem in that it's unstable and hard to understand. So what they did was they took, this is just a repeat of what we saw. There's nothing different here, just previously. So they took, and this is like the old way of doing things, where you have and this is for, you know, for these discrete, mostly being used for discrete, but also for continuous. And they have these, you know, sort of, they did some derivations and got these values for C skip and for C out and for C in. And then they have all these stability problems. And so they came up with this other idea, and we'll motivate this a little bit in a minute, to use cosine and sine, and this 1 over sigma d for the C skip, C out, and C in. And then when you plug that in, then you end up with this instead, right? So that nothing magical happened here. I'm just plugging my CF, my F theta. I'm just plugging in these values and I get this. Okay, so now this is the thing, and this is, in my opinion, the meat of the paper. So you have this part of you have this tangent function that I had called out, and this is like if you plug stuff in again into that tangent function, there's nothing magical here. I'm just plugging that cosine and sine and everything in there, and you get this big long thing here that's really hard to read. And in the paper they talk about, okay, this thing, if you look at just this thing, like the stability is instant, like this is not causing instability. This thing here is not causing stability. Oh, this part, like this sine times this expression is causing instability. So let's look there. Okay, so then they'd say, okay, when I, like this part is also not causing instability, it's this part, right? So we have the sine with a differential f. And then, so I take that and so now we're going to address all the sources of instability in these three, or not necessarily these three classes, but in this expression, right? So let's go through piece by piece and decide and figure out what is causing all of the instability. You'll notice this is the chain rule. I hope you guys are following. I'm trying to keep it very as understandable as possible. So any questions?
No,
Okay.
I was able to follow the last slide. Thank you for breaking it up and reminding us of the chain rule, RJ.
Yeah.
I think I'm going to start getting lost here, but you're doing great. You're doing a great job.
Okay, great, good. So this, and then the noise, this was just from the previous papers again. They just, you know, sort of give it to you and say, go read the paper if you want to know. And they have this C noise, which you'll recall appears here, right? This C noise, and this is basically just a way to a coefficient function that can like alter the time, like the rate at which time changes, basically. And they're saying this actually causes a lot of this, like definitely will cause stability at pi equals 2 because this is 0, and so therefore this goes to infinity. So definitely can't have that. So they just say, let's just set it to t. And they don't really motivate this except for this is just makes time pass at a constant rate, which makes, I think, intuitive sense. Okay, and then so that's like this C noise from this page. It appears here, it appears here, appears here, right? And then okay, so now what about this embedding thing? So what they say is This is sort of basically, similar to the Fourier. This is a Fourier embedding similar to what you have, in the positional embeddings in transformers. And there's a reason for that because this is used in the attention block. So they point out that, that the scale that they had set here was 16. It's very high and it causes lots of instability, including right when you get to pi over 2, it goes to infinity. So that's obviously bad. So they played with this and they, I think, empirically determined that, if we just make this really small to this value, I don't know where they got 0.2, but it just basically corresponds to the same positional embeddings that you see in the transformer. In attention is all you need. Hopefully that's also not so hard. I think they were very hand wavy, so I don't think.
So what they say is just set S to 0.02.
Yeah, that's right.
Man, I wish I had the math to understand how they got to the intuition, or maybe it's empirical, but okay.
I think they, I think that basically what it scales the coefficients to the same scale that the ones in attention is all you need are at. I think that's, and I think it's all algebra to do that. If I recall and understood correctly.
Thank you.
Yeah. And then this adaptive double normalization, I don't think it's that important. They didn't really talk, this is everything they say about it here. But that basically they just say, okay, there's this adaptive normalization, we think it works, but it doesn't work in our case, so we just do it twice and it seems to work. So no, I don't think we need to talk about it very much. So you can see like there's a bunch of stuff they're stacking on top of each other. Okay, and then there's this like tangent normalization. They tried this, and then they also tried just clipping to between -1 and 1. And they see like, oh yeah, like with our models, normalization has a lower FID score. This is Fréchet inception distance. It's a measure of quality of or closeness of perceptual closeness of images. So and so you can see, yeah, with either 2 steps or 1 step in our consistency model, then we do better, if we have normalization. And maybe if clipping might be good enough because it's obviously cheaper than doing this normalization here. And then finally, they have this adaptive weighting. Basically, I think all you need to understand is they throw this weight term, they throw the weight value into the loss function. So this is a loss function for the optimizer when they're, sort of doing the gradient descent. Then they throw this weight term in there. And that comes from somewhere right here, right? So this is our gradient, right? And this weight term isn't here. So they just when they derive the loss function, they just throw in that weight term, and that seems to help a little bit, right? This yellow, oh, no, actually, are they saying, no, it looks like it's better in some cases, but as you go, it looks like it's worse. Or no, I guess if you have if you do 2 steps, then it's worse. If you do 1 step, it's slightly better. So it doesn't look like it matters that much. And then tangent warm up, probably don't need to understand the sign t. They just put r in front of it, and that r just linearly increases from 0 to 1 over the first 10K iterations. And they just do this because it's unstable in the beginning. No need to discuss a lot. Okay, and so like when you stack all of these things together, then you're able to train much more effectively, and continuous time does much better than these discrete. So this n is the number of discrete steps that your model is taking. And maybe one interesting thing about this plot is that sort of best you can do is at 1024, and then it gets worse, right? So it goes, so it like gets better from here to green, and then green to purple gets way better, and then it gets worse again. So like at some point, the issues that they brought up start to matter.
Why is continuous so much better than discrete? Is it because it's just continuous and therefore it's easy to learn? But I thought the continuous was unstable as well.
No,
but
so
they made it
like
stable.
all of these techniques that we just talked about in the last few slides are making continuous stable. So then they are able to train more effectively. Yeah, I think that in the previous attempts, that actually other authors did, and they did, I think they found that they had to be very conservative in the, sort of like the way that they trained the model in order to avoid all the instabilities. And so because of that, they were not able to get good results. Whereas now they're able to, so like this intuition that they right here, that like this it's sort of like, because if I have only a few steps, the time delta is very big between these, then I'm going to have a lot of error in my tangent calculation, right? So this tangent is that tangent that we talked about. And if there's a error, like if there's a big quantization here, or like only a few time steps, then the ODE solver has to, sort of has only a limited amount of data to work with, and it ends up making mistakes due to that discretization. And so that it ends up having big errors and you get on the wrong trajectory.
That makes sense. That makes sense. Yeah, and we also have a question from the chat. What does the FID metric evaluate?
Yeah, that's a great question. I had to look it up myself because I've seen it before and I forgot it completely. It's so it is a numerical measure of the difference between two images. And the reason why it's popular is because it was explicitly designed to match closely to human perceptual difference, right? So there's a paper that talks about it, and one of the things that they talk about is, and I think it's definitely in the bibliography, but I can dig it if anyone's interested. It basically describes the previous methods that were being used, which were just like there was one of the divergence measures, or not measures, divergences. They didn't match to what humans actually were visually using to distinguish between images. So that this one was designed to do a better job of that. So it's supposed to be like a human perceptual distance metric between the input, like an input and output image. So I think that meaning actually I think there's like a, and I don't know exactly, that's a great question. I don't know exactly how they do the experiment. I think that they go do a forward pass with the image, and then they add some noise, and then they do the backwards pass, and they see the difference between the images. But I'm not 100% sure that does anyone know how this works exactly? No. Okay. Well, so yeah, that's actually that's something else that I want to follow up on. Okay. And then I talked about the tangent warm up, continuous versus discrete. Okay. So here's the part that everybody should be a little more comfortable with, hopefully, is just like we're evaluating models. You have this NFE stands for number of function evaluations. So this is how many times did my sort of core, how many iterations did I have to do to generate my images? And so and you see that all of their numbers in this section of the paper, they compare to 2 evaluations in 1, and they do slightly better whenever they do 2. So there's several things to note about this. One thing that they said in the paper, it's not here, but that it takes about 2x to compute to train this consistency model from as a distillation of whatever they distilled from. So approximately twice the compute. So if you spend a lot of compute to train a model and then you want to distill it with this mechanism, you're going to pay about twice as much. So that could present an operational problem, or it might not. Another thing to note, these joint training sections, these are basically GANs, but like you'll see some of the more common GANs here, and I don't know exactly the difference between these guys, but this CTM was the sort of overall winner for this CFAR data benchmark, and then for a conditional class ImageNet 64 by 64, it's a different one, but it's also in this joint training. So the GANs tend to be winning on these benchmarks. And so my belief is that these are the reason why people don't use them is because they're hard to train, and they have mode seeking behavior, meaning it's hard to get any diversity and hard to control them. But for these benchmarks, they do the best. And you see down here, sort of their consistency model is actually quite close for what it's worth. And then, so this is from distillation. And then this is if you train from scratch, then they do better. So that's maybe another interesting thing. So the distillation doesn't work quite as well as the training from scratch does. This is a place where someone might want to comment or ask questions. So I want to pause and make sure. Okay, so so they also compared this variational score distillation, which is kind of in the same ballpark in terms of effectiveness, and they found that they have or VSD has higher precision and lower recall, meaning lower diversity. And as the guidance scale gets higher, it does worse. And this, because if you'll notice the diffusion teacher model and the models that they built are very close to each other in these cases, both for precision and recall. So you end up having a very similar FID score as well. And then another interesting thing here, a couple of things. So their model does quite well when it's trained and not distilled. Let's see. The distillation doesn't do quite as well as the training. But neither of them do as well as the diffusion teacher, including the one that was trained from scratch. And that you'll see also interestingly, so the two-step does actually, the two-step trained model does worse with, sort of in the smaller models, but better in the bigger models. Okay, and then this is sort of their scaling study. We're kind of out of time, so I won't talk too much, but yeah, you can see they did well. They have up to 1.5 beam model. Let's see that's sort of the main takeaway. Okay, yeah, so that's all I have. I can take any questions if people want to stick around for a few minutes. I know this is not at all an easy paper.
I actually think it's one of the hardest papers.
Yeah.
I think the other one was probably PPO or DPO.
I missed that paper, so
yeah.
But yeah, and I mean, to me, this this was challenging for several reasons, right? Like one is just the topic, like diffusion by itself is hard. And then you have this like really obscure diffusion that is like even more complicated, and you have to understand a little bit about differential equations and whatever. And then on top of that, there's just a ton of literature to read in order to read the paper. So all those things like kind of, it's like a triple whammy. But I must say, I really enjoyed learning by reading, like, because I dug into all these papers, which I normally don't have time to do, but because I'm presenting, I took the time to really look at all the references and try to understand things well enough to hopefully explain them right to other people. And that was super valuable experience. And I'm glad I did that on such a hard paper. I hope that like, you guys felt that you got some of the intuition behind this. I know it's not easy. I tried to focus on the intuitions for the paper, and not so much on the math. So let me stop sharing. Okay, guys, if there's nothing else, I thoroughly enjoyed doing this. I hope somebody new will someone who's never presented before will take up the mantle for the next session or the next open session. That'll be awesome.
Yep, it's like if anyone has any paper that they want to cover, it's always great for y'all to voice out and say, because we always welcome new paper presenters.
Yeah, I think we had a volunteer for next week, but it's on the Luma. I don't remember which one it was, but people was signing someone up.
Awesome.
Yay!
More still needed.
Yeah. Okay, guys. Well, enjoy your Wednesday then. I'll see you guys on Discord.
Yep. Thank you very much once again for presenting.
Thanks,
No
RJ.
problem. My pleasure. Yep, you're welcome. Bye-bye.